Okay, so yesterday we were doing RSA crypto system. So encryption we said is message M to the E, where E and N are shared publicly. It is published on the site of the bank. So the customer simply computes her message raised to E mod N. Sorry? E comma N. What will be the encryption algorithm without E comma N? User should not know. No, but if the user doesn't know, how will the user compute M to the E? No, website as in the HTTPS web page will transfer this from bank to the customer. That can only happen through HTTP. I mean, or it can happen through other applications, but suppose you are not using your smartphone devices, then the only access is through the site globally. There is no other protocol that the bank supports. I mean, if there were other protocols that the bank supports, then you will have a problem checking whether it's the same bank. Then you might be sending your password to something else, right? Not your bank. That will be worse. So that is fast, and then decryption on the bank side is simply this C to the E inverse computation. That gives back M. So the security of this is based on inability of the adversary or the intruder to compute C to the 1 by E. For example, square root C. So I added this exercise that you can show that if you can compute square root of C mod n, then you can also factor in. Okay, so this is as hard as factoring numbers. And also it was pointed out by a student that if you compute phi of n, then you can easily factor in, because phi of n gives you p plus q, and n is equal to p times q, so you can solve a quadratic equation. So all these three problems are actually just the same as finding p and q, which is factorization. Okay, so this whole protocol is based on the hardness of factoring. And to study such things more and see other applications, we'll move to algebra, where we were studying the example of z/p. So z/p is the set of numbers 0 to p minus 1. But we have seen before that you can add them, you can multiply them, and you can also divide them, except division by 0. So this behaves very much like the real field, I mean the set of reals, set of rationals, set of complex numbers. It's more special than set of integers, because in integers you can't divide, here you can divide. And z/p star is a set which has many things missing. You cannot add, actually only addition is missing. You cannot add, but you can multiply and divide. In z/p star, can you negate? Can you multiply by minus 1? You can negate because multiplication is present, right? So for a there is also minus a, but the problem is that you cannot sum, because that is 0 which is absent. And similarly, if you look at z/n for composite n, then you can add, multiply, but you can't divide. Okay. Any questions at this point? You have seen these examples. So now what we will do is we will take it to a level of abstraction where everything looks the same. Okay, so reals, rationals, complex numbers, z/p, they all look the same at that level of abstraction. So that is called a field. So a set F with two operations which will always denote by plus and multiplication. But this is just convention. You could have called it any two operations. But since we want to stay close to the addition that you are used to, which is this real addition, we'll use the same notation as in your as you saw in school, plus and multiplication. So any set with two operations is called a field if these operations are nicely behaved, which is that for all elements AB in the field, A plus B is in the field, and also minus A is in the field. So we want 0 to be in the field and minus A to be in the field. Okay, these are the axioms associated with addition. So we are saying, first of all, we are saying that there is a special element 0 in the field. Second, we are saying that for every element A, there is a negation of A, which means that A plus that is 0. And third, we are saying is that any two elements can be added up to get a new element, a unique element A plus B in the field. So this is called the additive identity. And this is called the minus A or negative A, or maybe additive inverse of A. And this is called the sum, unique sum. Okay, is that clear? So that is just think about real numbers or even integers. That's the property we want to abstract out. So remember that F is an arbitrary set. It can be anything, right? It can also be a set of animals, for example. And then you can define addition to be something arbitrary. As long as it satisfies these axioms, it will be called addition on the cows. Okay, F is not really numbers. It can be anything. One more serious example is that it can be very non-number theoretic, like it can be a matrix. Right? So matrices are complicated objects. They are far away from numbers. But you can add them, they have an additive inverse, and there is a zero matrix. So the definition doesn't demand any other property on the set except this. And for all AB, so the same AB, for all AB, now A star B should be an element in F. There should be a multiplicative identity 1 in the set, and if A is non-zero, So if A is not 0, then A inverse should also be in F. Okay, so that is the, these are the axioms for multiplication. So that's the unique product. This is the multiplicative identity. And this is the multiplicative inverse. Is that clear? So this mimics the multiplication of real numbers that you are used to. And finally, you want these two to interact, which is the distribution rule. So multiplication should distribute on plus. What does that mean? So this means that if you have A star B plus C, then this should also be AB plus AC. Okay. What about plus distributing on star? Will that make sense? So A plus BC, we don't have any such property in real numbers, right? A plus BC is not equal to A plus B times A plus C. So we stay away from that. We only say that star distributes on plus. And fourth is not very important for you, but still you might want to remember that, or I should note that plus and star, they commute. So plus and star are commutative operations. Which means that A plus B is B plus A, and A star B is B star A. Okay, this is also called abelian. So in a field, the operations, we only commutative or abelian operations are allowed. So you can add in any order and you can multiply in any order. And for the plus, the first set of axioms, multiplication is similar except that you exclude 0 for inverse. Don't do division by 0. And third is the distributivity. So any set with such operations is called a field. Is that clear? Okay, so yeah, so we'll suggestively call these operations addition and multiplication, although they may have nothing to do with real addition multiplication. Right? You can come up with strange operations also. But anyways, to give examples of this, what are the examples of fields? So F equal to, the smallest field you can think of is what? Yes, that's a fair field. Right, so element, well, the problem is we have said we want 1 also. Yeah, but we have said that 1 is in F. So just by that, conventionally we are not calling it a field. Let's not take that. Uh, the smallest field you can think of is the field of rationals, which is fractions of integers, right? Because you can see that in rationals you can add, well, first of all there is 0, there is 1, you can add, you can multiply, you can divide, and distribution is also there, commutativity is also there. So everything is satisfied. So this with the usual plus star is a field. Similarly, real numbers and then obviously complex numbers. So these are the natural fields, right, that you have worked with without knowing that these are fields. What else? So a new field that you have seen is Z/P. This is a field for prime P. Right, because there is 0, there is 1, you can add, you can multiply, you can divide, and there is this distribution. So this is seen before. You can check all the axioms, everything will work. So this is a more unnatural field, and in particular it's a finite field. There are only P elements, 0 to P minus 1. But still you have a way to add them. So you can even add big numbers like P minus 2 with P minus 1. So you go out of the set, but then you come back by division. Right? And similarly, you can multiply big numbers, you get a bigger number, but then you come back in the set. And inverse and everything. So what happens if you look at composite n? Is this a field? Why not? Is it not a field for every composite or only for some composites? Yeah, so you can show this as an exercise that for any composite number, this addition multiplication which is well defined, the problem is in division. Okay, you cannot divide, there will be some number whose inverse will not be there. So this will not be a field. This is never a field. So for example, if you take 8, then mod 8, you cannot inverse 2, 4, 8, 6, and so on. So this is true, the field property is true only for prime numbers. Okay, so there is, let's see how much you understand this. So F is a field. In any field F, 0 inverse does not exist. Can you show this? Can there be a field and then it will have 0, where 0 inverse is a number, is an element in the set? Is it ever possible? Is there any field where division by 0 is allowed? So suppose it is, suppose there exists an A in F such that A times 0 is 1, right? What can you deduce from this? Yeah, so then this means that 0 is equal to 1, which means what? What happens if in a field 0 is 1? So this means that whatever element you take in the field, b times 0 is b times 1, right, which means that b is 0, which means that the field can only be a singleton, that is 0, which is not a field. Is that clear? Yes. A into 0 is, yes, that's a good point. Yeah, so you are good with axiomatic proofs then. How can I say that A times 0 is 0? This is not anywhere in the axiom. Yeah, so you have to use distributivity. This is why the axiom was put there. Without distributivity, you cannot deduce A times 0 is 0. So you use distributivity axiom, and from there you will get this. Let's do it separately. So A times 0 plus 0 is equal to A times 0 plus A times 0, which means, so in the beginning it's A times 0. Now you can use the property that in the field A times 0 is an element. It has an inverse. You can add both sides, and you can deduce that 0 is equal to A times 0 for all A in the field. Is that clear? So that's the distributivity axiom and negation. Is that clear? So those are the things. It will seem suggestive that of course A times 0 has to be 0, but then since your set is not a set of numbers, it's something abstract. So all you are allowed to do is deduce from these axioms. Okay, so you have these axioms in red, and you have your common sense, which is basically modus ponens. And from that sequence of implications, you deduce what you want to deduce, or you have to give a counterexample, which means you have to construct a field where something is false. Right? So either you give a commonsensical proof using the axioms, or you construct a counterexample. Some of these things will be hard, especially in the exams or even quizzes. But this is the first step towards abstraction. So with this you can give proofs which hold for things which are very far away from numbers and even far away from matrices or vector spaces. They can be completely abstract mathematical objects. Okay. What about the set of integers with the usual addition multiplication? Is this a field? This is also not a field. Why? Division is not there, right? So what are the elements in this in the set of integers which have inverses, multiplicative inverses? Yeah, it's only plus minus 1. So that is the proof. So only plus minus 1 in Z has multiplicative inverse. So it is something which is just below fields. It's not as good as a field, but it's comes quite close. Everything else it has. Okay. Another property is that in a field F, AB is equal to 0 if and only if A is equal to 0 or B is equal to 0. Can you show this? So clearly if A is 0 or B is 0, then you can deduce AB is 0. That's the above proof. What about the converse, which is AB is equal to 0? What can you deduce from there? AB is equal to 0 implies? Exactly. So if AB is 0 and A is not 0, B is not 0, let's assume all these three things for the sake of contradiction. Or maybe actually we could also just cleanly do it by no, let's keep this way. Just the first condition. So if AB is 0 and A is not equal to 0, then it will have an inverse. So you can multiply by A inverse. Both sides, and then you use the definition of inverse, which is A inverse times A is 1. So 1 times B, and you have already deduced that anything times 0 is 0, so you get B is equal to 0. Okay, so either A is 0, in which case you have the result, or A is not 0, in which case B will be forced to 0. Right, so this cancellation rule is there in fields. The same thing as you have in the field of reals. You can cancel and deduce something about factors. Any questions? Yeah, okay, so you are asking for more axioms. They didn't want to give them. But there is another axiom which is implicit. I did not want to load you with definitions. These operations are associative. So associativity means that if you are multiplying, let's say, or you are adding three things, then it doesn't matter in what order you add. So A plus B plus C, you can first do A plus B, then C, or you can first do B plus C, then A. Same thing with multiplication. So this is why we will not use parenthesis because it doesn't matter in what order you do the computation. You do the sum or you do the multiplication. It's only for distribution that we will use parenthesis, because we have to specify whether A is multiplying only B or is it multiplying B plus C. Okay. So I'm not writing this, it's not very important. But since some students are curious, operations will be assumed associative and commutative. But that is pretty natural, the same thing as in reals. So here, for example, we have done the following. So we are first computing A inverse times A, and then we are multiplying the answer with B. It will be the same as the other option, which is I compute A star B. If we first multiply AB and then multiply that with A inverse, it's the same. This is the associativity axiom. So in the absence of any parenthesis, it is just assumed that you can do whatever you want, whatever order. Because there is associativity and there is commutativity, so you can also flip. You can also say that I will first compute B star A and then I will multiply by A inverse, or I'll first compute B star A inverse, then I will multiply by A, or whatever, doesn't matter. All these values are same by the axiom of field. Is that clear? But yeah, this is important, although not important in this course, but it's important in algebra in general, because algebraists study all possible combinations of these axioms. Okay, so everything is known. You can remove distributivity, you can remove commutativity, you can remove associativity, you can remove 0 or 1, you can remove a whole operation, and then there is only one operation, and so on. Okay, every object has a name and it's studied. Every object has multiple books studying it. One of those we will do after a few lectures. But any combination of axioms has a life. Okay, so next property of a field is what is called characteristic. One more example we can afford. So n by n matrices on, sorry, the multiplication what? Commutes. No, but the definition doesn't tell you what multiplication and addition operations are. There can be anything. In certain situations, multiplication can be doing addition and addition can be doing multiplication. Or it can be doing something completely crazy. Like in Boolean algebra, you can do OR operation, and multiplication can be the AND operation. So there is, the axiom doesn't assume what the set is and what plus n star are. This is just a suggestive notation, and it is very easy for me to confuse you. So the only correct access you should have is through the axioms. You have to remember these axioms, that what it is supposed to do. So it's not about what it is, but what it does. That you can only see in examples. By itself, f is nothing, but we are listing a set of properties whatever object satisfies these properties is of interest. In fact, yeah, so that was the example I was going to give. So for n by n matrices doing addition and multiplication, what are the things in the axioms that are missing? The set of axioms or the set of properties that a field should have, that a set should have, in this set of matrices, what do you think is missing? Yeah, so in this case, multiplication you know how to do, but you also should remember that it's non-commuting, right? So A times B is not the same as B times A. So that is one thing which is missing. What's the other thing? Yeah, so multiplicative inverse is missing. And commutativity is missing. So it's non-commuting multiplication. Anything else? So everything else is there except these two axioms. That multiplication doesn't commute and multiplication will not have inverse, right? So here multiplication is essentially the problem. It's not a field. Okay. So I don't want to give the axioms again, but such things where you have all these axioms which this set of matrices satisfy, it's called a ring. Okay, so it's not a field, but it's a ring. So a ring basically has to satisfy most of the axioms, but not all. So you can, all the axioms for addition should be there, associativity should be there. For multiplication, everything except inverse should be there. Distributivity should be there. Commutativity should be there 50%. So for addition it should be commutative, for multiplication it may not be. Okay, so part of these axioms in this way give you a ring. So every field is a ring, but every ring is not a field. Okay, ring is something more relaxed. It's closer to a set. In fact, it's closer to a vector space. So there is a lot of structure, but not so much as in a field. Okay. Another example of a ring. Is Z a ring? So Z also has addition, multiplication, and most of the axioms. So interesting examples are Z, and similarly the Z/N ring. It's a ring for all n. Okay, because you can do, basically you can do addition, multiplication, also both are commutative, associative. Distributivity is there. The only thing that is missing is inverses may not be there, multiplicative inverses. 0, 1 is also there. So these are one of the nicest rings. and we'll see one more fundamental ring in a short while. But before that, let me define characteristic. So characteristic of a field is what? Have you heard about this term? What is characteristic of a field or a ring? So this is the smallest number such that if you add 1 that many times, then it vanishes. Is that clear? So will this n always exist? Can you think of an example of a field where this n doesn't exist? Let me add this positive condition. So will this always exist? A positive integer? For example, in reals it's impossible. If you keep adding 1, then it will never vanish, right? It will just keep getting bigger and bigger. Same in the field of rationals, reals, complex, right? If you add 1, it just gets bigger. But when it exists, then we call it characteristic. If it doesn't exist, we call it 0. Because 0 times 1 is 0. So if it doesn't exist, then define it to be 0. Okay, so characteristic is this. So for example, characteristic of reals so rationals, reals, complex. These are all 0 characteristic fields because there is no smallest positive number equal to 0. And on the other hand, characteristic of the Z/P for a prime P field is what? This is P. Right, so this is the difference between these finite fields and infinite fields, or the real kind of fields. The real fields have characteristic 0, while these unreal fields have characteristic of prime number. Okay, so next property. So the first property you can show for characteristic is for finite field F, the characteristic is positive. Can you show this? So as long as the field is finite, there is always a characteristic. There is always a smallest positive n such that n is 0. What is the proof? Exactly. Yeah. So, I mean, since there are no infinitely many elements, so what will happen is that um, after a point, so say suppose this n doesn't exist. Then what it means is so you keep adding 1 what can you say about this? So maybe, yeah, we have to look at different elements. So let's look at 1, then 2 times 1, 3 times 1, and the size of the field times 1. Right, so these are the elements. Field f is finite, so this is a finite set. Or maybe one more. So what can you say about this set? It has more elements than the field. Right, so 2 of them are the same. Is that correct? By pigeonhole principle. Has a repeating element. Which means that there exists AB positive natural such that A times 1 is B times 1 in the field, which means A minus B times 1 is 0, right? Which means that the characteristic does exist. So it's in fact a direct proof. We didn't need to do the contradiction thing. You just consider this set, and from here, since 2 elements are the same, field was finite. So A minus B in particular, you can assume it to be A greater than B. And so A minus B is a positive natural number. That times 1 is 0. Is that clear? So the smallest n will exist. It's positive. So I should not actually do this. Consider these sums, these are 1 more than the field, so 2 of them will be equal, and then you get direct proof. Okay. So what is more interesting is that the characteristic of a field is always a prime number. So either the characteristic is 0 or prime. Okay, so these examples that we saw, rational, real, complex, characteristic being 0, and characteristic of z/p being p, which is a prime. These are the only case. These are the only values. You can only get characteristic 0 or a prime number. So suppose characteristic is not 0. If it is 0, then you are done. If it is not 0, how do you show that it's prime? Yeah, so let's say the characteristic is n as above in the proof above, and say it factors. N is equal to p times some m. Both of them are actually greater than 1. Okay, so suppose n is not a prime, which means that it will have two factors, both of them greater than 1. Right, this is exactly the meaning of composite n. What now? What is the proof you were saying? Yeah, so by definition n into 1 is 0, so you write now m1 times m2 times 1, and you if you see the following, what can you deduce? Or maybe even simpler, let's not do all this. Let's just use the cancellation property. AB is equal to 0 means one of these is 0, right? So if you use that, then you will deduce that M1 is 0 or M2 is 0. Which will be a contradiction. Is that clear? Yeah, so the question is it different? Why is it different? So we have put 1 here. Yeah, that's a good point. So there is a 1 sitting here, right? This 1 is from the field. So it's true that M1, M2 are numbers and the field F may not have numbers. It may have arbitrary things. But then, see your point. Yeah, so let's do the older way. We have to do like this, yeah. So then, so M2 times 1 is an element in the field. It's just 1 added M2 many times. And then that number is added to itself M1 many times. And you get 0. So what do you deduce from this? So the bracketed part, that is a field element, right? So you can invert it. When can you not invert it? When it is 0. So either that is 0 or it's invertible. This exists. Now, if it is 0, then what happens? That's a contradiction to the characteristic n being the least. So it's not 0, so it's actually invertible. Which means that m1 times m2 times 1 times its inverse. It may be a good idea to give this a name. It's getting too long. So it's a field element, let's call it U. So you have m1 times U inverse equal to 0. Which means that m1 is 0. m1 times 1 is 0. Which is a contradiction. This was a bit long, but if you want to do it properly, just following the axioms without using any intuition, without using any real intuition, then you have to do it as follows. You have to write m2 times 1, that's the field element, call it U. So m1 times U is given to be 0. Either U is 0 or it's invertible. If it is 0, you have a contradiction to the characteristic n. Why? Because, well, m1 and m2 were smaller than n, right? They are factors, so they are less than n. So U cannot be 0. If U cannot be 0, then you can multiply by U inverse and you will get m1 times 1, 0, which will again contradict characteristic equal to n. Is this clear? Sorry? No, we have said our convention is that 1 is also always there. That is true. Yeah. If you think about it that way, then, but that is not related to this, is it? To this proof? Yeah, so we can say that. We have to go back. But here I had said that f equal to 0 gives a contradiction. So anyways, this you can work out. So let me just add that in the next page. So f equal to 0 with addition multiplication is also a field with 1 equal to 0. But you have to be careful here. I mean, you have to note here that 0 has an inverse, which is itself. So only this field has that weird thing, which is why I didn't want this to be a field. But if there are philosophical objections, we can make it a field. That's fine. We are just saying that 0 and 1 they are equal. So then everything in the field collapses, and there is only one element. That's 0. Okay, what is the characteristic of this? Yeah, so characteristic exists here, and that's 1. So this has very weird things. Yes. Yeah. No, so then you have to modify it by saying that the only field where 0 inverse exists is f equal to 0. Everything collapses in that field. Let me not do it here. I mean, this is anyways a very pathological example, because the characteristic here is also coming out to be 1, which in a way is a prime number, so I guess it's fine. So we have shown this theorem that for any field, characteristic is either 0 or prime. Any questions? Why not? I say it is. See, these are definitions we can change. Usually it is said that a number is prime if only 1 and itself divides it. It's true here. Yes? Okay. Yes, so what then we have shown is that for every number including 0 and primes, or let me write that actually, for every n which is 0, 1 and prime numbers, there exists a field with characteristic n. Okay, so namely for 0 you have rationals, for 1 you have just the 0 field, for prime p you have z/p, and we have also shown the converse, that for every field these are the only options for the characteristic. Right, so that was, let's call this lemma 1. And this is the construction or examples. Right, so that you know that this concept is not vacuous. For all these numbers there are fields, and for every field there are these numbers. Right, so we have kind of a good understanding of field vis-a-vis characteristic. And that brings us to the definition of the most important field in computer science, which is the Galois field of size p. So this is the finite field of size p for prime is denoted Fp, which is just the set z/p with plus multiplication. It has characteristic p, size p, and all these operations are present. So it's a famous finite field. It is also called prime field or Galois field. So we are just defining this notation basically. From now on, when I say Fp, I will not just mean the set z/p, but the whole structure that comes with it. Okay, that's the, and then we can do arithmetic over that. So one question that we can immediately ask is, is this the only field with characteristic? Actually, first question you can ask is this the only field with size p? Or are there other fields of size p? What do you think? This should be easy. There cannot be any other field because this field is generated by 1. You are just adding 1 p times, right? And you get all the elements. So any field of characteristic of size p, since p is prime, it will also have characteristic p, and so it will be exactly this. There is no other option, right? So it's the only field of size p. This you can prove as an exercise. Is the unique field of size p. And the next question is, okay, size is settled. What about characteristic? Are there other fields of characteristic p? That we will settle in the next classes. Are there other finite or otherwise finite fields of characteristic p? Right, so we have constructed and defined one field, and that's unique if you look at size p. But then for size, for other sizes but the same characteristic, are there other constructions? So we'll do that next time.